Have you ever had that really specific frustration where you try to use an AI for actual heavy lifting research and it just falls flat?
Oh, absolutely. You mean beyond asking it for a cookie recipe or, I don't know, the capital of Peru?
Exactly. I'm talking about a real thorny question. The kind where you need to check 3 different sources, compare dates, maybe read a footnote or two.
Right, the real work.
Yeah, you ask the AI, or what happens. It either gives you this incredibly generic surface-level summary that tells you absolutely nothing, or worst, it just hallucinates.
Oh, yeah.
It makes up a fact that sounds completely plausible but is totally wrong.
It's the lazy student syndrome. It feels like asking someone to write a thesis and they just skim the Wikipedia intro, bold a few words, and go to lunch.
That is exactly what it feels like. And it's
Yeah.
maddening because, I mean, we know these models have read the entire internet.
Right.
So why can't they connect the dots?
Well, it comes down to what's called the information-seeking bottleneck. Large language models they're fantastic at reciting what they've already memorized.
Right, the trivia.
Exactly. They are great at pattern matching, but they are surprisingly bad at the actual process of research, like the hunting, the gathering, synthesizing new information from the live web.
Well, today we are doing a deep dive into a research paper that claims to solve exactly that frustration.
Yes.
It's titled WebExplorer, Explore and Evolve for Training Long-Horizon Web Agents. And our mission today is to look at how researchers are solving this information-seeking problem.
And it's a really exciting piece of research because it flips the script on how we usually build smarter AI.
How so?
Well, normally when an AI company wants to make a model smarter, the answer is just, build a bigger brain, add more parameters, buy more GPUs, spend more billions.
Just brute force it.
Exactly. But this paper argues that we don't need a bigger brain, we need a tougher gym.
I really love that analogy. And the headline here is pretty wild. They took a relatively small model, just 8 billion parameters.
Which is tiny by today's standards.
Right. And by training it in this new gym, it managed to beat massive models that are nearly 10 times its size. So it's this total David versus Goliath story.
It is. But what's even more fascinating to me is the methodology behind it. They essentially taught the AI to teach itself how to research.
That sounds like science fiction.
I know, but they created a system where the AI generates its own training data. And that data is specifically designed to be just headache-inducing hard.
So before we get into the how of it all, let's unpack the why. Why is this so difficult? I mean, you or I can use Google, we can click links. Why can't a super intelligent AI figure out how to browse the web?
It comes down to what researchers call long horizon tasks.
Define that for us.
Sure, if I ask you who won the World Cup in 1950, that is a short horizon. It's one search, one click, one answer.
Simple enough.
But if I ask you a question that requires you to find the winner, then find the referee of the final match, then find out what club that referee became the chairman of later in life.
That's a lot of steps.
Right. That is a long horizon.
It's a dependency chain. You need the answer to step 1 to even know what to search for in step 2.
Exactly. You have to reason at every single step. You have to search, read, understand, decide what to search for next, click a link, read again, and keep that whole context in your head without getting distracted.
Which is hard even for us.
It really is. And the current benchmarks for testing this are brutal. There's one called Browse-Compin.
Okay.
It's a set of questions designed to test these web agents. And here is a pretty sobering stat from the source material. Human annotators, actual people, fail to answer these questions over 50% of the time.
Wait, hold on. Humans fail half the time.
Even when they're given 2 full hours to try.
2 hours? Just for one question?
Yes. That is how complex these queries are. They aren't just trivia, they are deep investigations. So if humans struggle to keep the thread, you can imagine why an AI, which is essentially just predicting the next word based on probability, falls apart. It just gets lost in the weeds.
That really puts it in perspective. So, I mean, the obvious solution would be, okay, let's just show the AI thousands of examples of how to do this correctly.
Teach it by example.
Yeah, exactly. But I'm guessing that's easier said than done.
Precisely. We have a massive data deficit. To train a model to do deep research, you need training data that shows the step-by-step process of deep research.
Right.
But since humans struggle to do it, it's incredibly expensive and incredibly slow to pay people to sit there and create that data.
And what about the stuff that's already out there on the internet?
It's mostly too simple. It's simple Q&A, how to boil an egg, or previous attempts to generate synthetic data resulted in questions that were just weirdly complex in an unnatural way.
Like what?
Like asking an AI for a list of 50 items with highly specific arbitrary constraints.
Oh.
That doesn't teach the AI reasoning, it just teaches it fetching.
Okay, so we need data that forces the AI to actually think, to explore, and connect the dots. But we can't afford to have humans sit around writing it. Enter WebExplorer.
Enter WebExplorer.
How does this system solve the problem?
They developed a brilliant two-step process to manufacture this data automatically. They call it explore and evolve.
Let's start with phase one, exploration. Or, as I like to call it, the wandering phase.
That's a perfect name for it. The goal here is to build a knowledge graph, a web of connected facts without using strict, rigid rules. They basically just let an LLM loose on Wikipedia.
They start with a seed entity, right? Just a random topic.
Correct. In the paper, they use the example of the Brazil national team.
Okay.
They give this seed to the AI and just say, go learn stuff, click links, find connections.
It's exactly like falling down a Wikipedia rabbit hole at 2 in the morning.
Yes.
You start looking up a soccer team, and an hour later, you're reading about the history of rubber production in the Amazon.
That is literally the mechanism at play here. And the paper traces a really specific, fascinating path the model took during this phase.
Walk us through it.
So it started with the Brazil national team. That led it to the 1950 World Cup. From there, it found the final match. Then it zoomed in on the referee of that match, a man named George Reader.
Okay, so we're at a British referee in 1950.
Then the model found out that George Reader later in life became the chairman of Southampton FC, a football club in England.
Right.
And then it connected that to Southampton winning the FA Cup in 1976.
That is quite a journey. From Brazil in 1950 to Southampton in 1976.
It is. And once the model has explored this path and verified all these facts, it generates what they call a draft question.
They call it Q0 in the paper, right?
Exactly. And it basically says, identify the referee of the 1950 World Cup final, who later became chairman of the club that won the 1976 FA Cup.
See, to me, that sounds like a pretty good trivia question already. But according to the paper, that's not good enough.
No, it's not. And this is where the evolve phase comes in.
Phase 2.
Right. The problem with that draft question is that it's too keyword heavy. If you search referee 1950 World Cup final chairman Southampton, Google will give you the answer instantly.
Ah, I see. It doesn't require the AI to reason. It just requires the AI to search keywords. It's too easy to cheat.
Exactly. So they developed this iterative query evolution process, and this is really counterintuitive. Usually to make a prompt harder, you make it longer, you add more constraints.
Right, you add more rules.
But WebExplorer does the exact opposite. It makes the question shorter, or at least much vaguer. They call it long to short evolution.
So they're obfuscating the clues.
Yes. They use techniques like remove salient info, where they just delete specific years or names.
Yeah.
Or strategic obfuscation, where they replace a proper noun with a description.
So instead of Manchester United, they might say a first division giant.
Spot on. Let's actually look at the example they gave, because this really clicked for me when I read it. The easy version, the draft, was essentially a football match took place, referee was oldest person, chairman of club that defeated Manchester United, player died at age 44.
Right, it has Manchester United, died at age 44. Lots of highly specific hooks you can just copy-paste into a search bar.
Too easy. Now listen to the evolved version that the system created from those same facts.
I have it right here. It says, in the unique FIFA World Cup tournament, match official guided a second division club to victory in the Monarchs' final attendance, hailing from a district that joined a centuries-old Royal Naval stronghold.
Do you see the difference?
It sounds like a riddle from a fantasy novel. The Monarchs' final attendance. A centuries-old Royal Naval stronghold.
Exactly. You cannot Google that sentence.
Bro.
If you search that whole string, you will get nothing. You have to break it down logic puzzle style.
So how would an agent even solve that?
Well, step one, it has to figure out which World Cup format was unique. That implies the 1951, because it was the only one without a traditional knockout final.
Okay, then step 2.
Who was the official? That's George Reader. Then step 3, what is the Royal Naval stronghold? That turns out to be Portsmouth.
So you have to solve the question before you can even search for the answer.
It forces multi-hop reasoning, and they generated about 40,000 of these pairs.
40,000 riddles.
Yes. This data set, WebExplorer QA, is the tough gem we talked about earlier.
So they have this killer data set.
Yeah.
Now, how do they actually train the AI? You mentioned a 2-step training process.
Right. Step 1 is the cold start,
Which is,
supervised fine-tuning. Basically, they show the model the data set, the complex question, and the correct path to the answer and say, here's how you use the search tool and the browse tool to solve these riddles. It's teaching the mechanics.
It's like showing someone how to use the weight machines before letting them loose in the gym.
Exactly, just making sure they know the form. But the real magic happens in step 2, reinforcement learning.
Yes, dance, Jim.
Yes. They used an algorithm called GRPO, Group Relative Policy Optimization.
That sounds incredibly technical.
It does, but the concept is actually quite simple. In this phase, they don't tell the model how to solve the riddle. They just give it the question and say, go, find the answer.
And if it does?
It gets a reward. It gets points for correct formatting, about 20% of the score, and points for getting the right answer based on an automated judge.
So it's high-stakes trial and error.
Very much so. And they did something very smart here with what's called curriculum learning.
Meaning they ramp up the difficulty over time.
Precisely. They started easy. They gave the model a context window, its short-term memory of 64,000 tokens, and allowed it to take 50 turns.
50 turns. So that means it can perform 50 distinct actions like clicks, scrolls, searches.
Yes. But as the training went on, they ramped it up. They increased the memory to 128,000 tokens and the allowed turns to 100.
Whoa. 100 turns.
Sure.
That's like letting the AI click 100 different links to find one single answer.
And here's the fascinating part. The model actually needed it. They found that as the model got better, as it got smarter, the average number of steps it took actually increased.
Wait, increased?
Yes. It went from taking about 11 steps to over 16 steps on average to solve a problem.
That is completely unexpected. Usually in the tech world, optimization means getting faster. You think getting better means getting to the answer quicker.
Yeah.
But here, getting better meant being more thorough.
Exactly. It learned chain of thought reasoning. It learned that to answer the Royal Naval Stronghold question, it couldn't just guess or take the first Google snippet it saw.
It had to verify.
Right. It learned to be patient. It learned that taking 20 steps to be right is way better than taking 5 steps and hallucinating.
That's a really human lesson, isn't it?
Yeah.
Measure twice, cut once.
It really is. It learned diligence.
So the million-dollar question, did it work? They built this incredibly tough gem. They forced the AI to solve these insane riddles. How did it stack up against the big guys?
The results are honestly shocking. They compared their model, WebExplorer 8B.
Which again, is 8 billion parameters, considered very small in today's landscape.
Right. They compared it against WebSailor 72B, which is a massive model.
Okay, the Goliath.
Yes. And on the Browse Comp benchmark, that really hard one where humans fail half the time, the big 72B model scored 12%.
Okay, 12%. That's pretty low, but we established it's a brutal test. And the little guy, the 8B model.
15.7%.
Wow. So the small model didn't just match the big one. It beat it by a significant margin.
It beat it handily. And on the Chinese version of the benchmark, Browse Comp, the gap was similar. 32% for the small Web Explorer versus 30.1% for the giant model.
That completely validates the whole David versus Goliath narrative. It's not about the size of the brain. It's about how well you've been trained to use it.
And it suggests that for specific skills, like deep research and web navigation, specialized training data, this synthetic, self-generated data is far more valuable than just raw model size.
Right, because you can have a giant brain, but if you don't know how to navigate a library, you're useless.
Exactly. This small model knows how to navigate the library better than anyone else right now in its weight class. It's state-of-the-art for anything under 100 billion parameters.
There was another benchmark mentioned in the results that I thought was really telling. The HLE, or Humanity's Last Exam.
Which is a very dramatic name.
Oh, terrifying name. But it's a benchmark full of incredibly difficult questions across STEM, humanities, math, everything. Now remember, WebExplorer was trained mostly on Wikipedia-style knowledge.
Right. It wasn't trained on advanced calculus or physics specifically. It was wandering around finding soccer referees and rubber plantations.
Exactly.
Okay.
But on the HLE benchmark, WebExplorer 8B still outperformed other models in its class.
Yes, it did.
So wait, it got better at answering questions it wasn't even trained on.
Yes. And that is the true aha moment of this whole paper. It didn't just memorize the facts about Southampton FC. It learned the skill of research itself. It learned how to find an answer.
And that transfers?
Precisely. If you know how to use a library to find obscure football statistics, you also know how to use a library to find physics constants. The underlying skill is exactly the same.
That is profound. It's the difference between teaching a student facts and teaching a student how to learn.
Exactly. And this paper proves that we can automate that entire teaching process. We don't need thousands of humans writing riddles.
The AI can write the riddle.
And then the AI can solve the riddles.
Right.
And in the process, it becomes a better researcher.
So let's bring this all back to you listening. What does this actually mean for the future of AI tools? Because right now, if I want to do deep research, I still feel like I have to do all the heavy lifting.
I think we are on the cusp of a major shift from search engines to research agents.
Okay, what's the difference?
Right now, you are the agent. You type a query, you read the page, you synthesize the info, you type a new query.
You do the iterating.
Right. This WebExplorer architecture shows a path where the AI can reliably take over that loop. You give it a vague, complex goal, and it actually has the patience and the reasoning skills to spend 20 minutes or 100 turns tracking it down for you.
And doing it on a model small enough that it doesn't cost an absolute fortune to run.
That is the key. 8 billion parameters is small enough to run on consumer hardware or very cheaply in the cloud.
So we aren't talking about needing a supercomputer anymore.
No, we are talking about highly accessible, expert-level research capabilities for everyone.
It really challenges the whole idea that bigger is always better in AI development.
It proves that better data is better, and if we can synthesize that data autonomously, the bottleneck for AI improvement isn't computing power anymore, it's just our imagination in designing the curriculum.
So we've got a small model, training in a gym of its own creation, solving riddles that stump humans, and beating giants in the process.
It's a pretty compelling argument for the future of synthetic data.
It really is. Okay, before we sign off, I want to leave everyone with a thought to chew on.
Let's hear it.
We talked about how this AI generates its own questions, these really complex riddles, to train itself. And we know that as it gets smarter, it needs harder questions to keep learning.
Right, the curriculum has to scale. You can't stay on the beginner weights forever.
So imagine this loop running for a few years. The AI generates a curriculum that is so complex, so full of obscure connections and long horizon logic that no human could ever write it.
Okay.
And then it trains itself to solve it. Are we approaching a point where the training process itself becomes completely incomprehensible to us?
Wow.
Like where the AI is studying a textbook written by an AI for an AI in a language of logic that we can barely follow?
That is a fascinating and, frankly, slightly unsettling thought. We might literally building a self-sustaining cycle of intelligence improvement that just leaves us as the observers.
Definitely something to think about the next time you fall down a Wikipedia rabbit hole. You might just be training your own neural net. Thanks for taking this deep dive with us into WebExplorer.
Pleasure as always.
See you on the next deep dive.